This is the notes page for rational functions, and this time we are going to be looking at slant asymptotes. So I just highlighted from the other notes, number 5, to find a horizontal asymptote, remember you have to look at the degrees. And if you have the same degree on the top and the bottom, then there is going to be a horizontal asymptote, and it'll be y equals leading coefficient over leading coefficient. If you have a degree small over large, then this denominator is going to get huge for large values of x, so y is going to equal 0 will be your horizontal asymptote. But if you have a degree large over small, then there's not going to be a horizontal asymptote because this numerator is going to get bigger at a much faster rate than the denominator, and the y value will keep increasing, so you'll have a slant asymptote. And sometimes you have to use either long division or synthetic division to find it. Okay, so we'll start with this first one. It is going to have a slant asymptote because it's got degree 2 over degree 1, but let's go back and review. So you start at the beginning. Remember, you have to factor. So this numerator factors into x and x. The factors of 30, 1 and 30, 2 and 15, 3 and 10, 5 and 6. That subtract to be minus 1 would be x minus 6, x plus 5 over x minus 6. So first you factor, then remember, before you cancel anything, you have to find the domain, and that comes from the denominator. And we can see that x cannot be 6, so you've got a restriction, and the interval notation would be the domain is all the x's from negative infinity to 6 union 6 to infinity. Now, after you write the domain down, then you can cancel, and I like to write my reduced function down because everything else can be found by looking at the reduced function. Okay, so remember, wholes can happen if you have a factor in the denominator that cancels, and this factor cancels, so this restriction is going to show up as a whole, which is an ordered pair. So the x-coordinate would be 6. We'll just go right here to the reduced fraction to find the y-coordinate partner. 6 plus 5 is 11, so there's a whole at 6, 11. That was the only factor in the denominator, so in this one there is no vertical asymptote. Okay, so the slant asymptote, something interesting is happening here. What you have to do is you have to use either long division or synthetic division. So you're going to divide x minus 6 into x squared minus x minus 30, and I'm using long division here first just to review it. So x squared divided by x is x, and then multiply it back out. That gives you x squared minus 6x. Draw your line, change the sign. These cancel, and these give you 5x minus 30. 5x divided by x is 5, and then distribute, and you get 5x minus 30, and you have a remainder of 0. Now the remainder is 0 because you can see that there was a factor x minus 6 in the numerator, so x minus 6 goes into it perfectly, but that's not always the case. For slant asymptotes, you might have a remainder, but we don't ever worry about the remainder because the horizontal and the slant asymptote are talking about as x gets really, really, really big. As x goes to infinity, what's y doing? As x goes to negative infinity, what's y going? So remainders of small values don't really matter when we're talking about large values of x. Okay, so anyway, don't worry about the remainder. The quotient is where your slant asymptote comes from. Don't just write x plus 5. That's an expression. An asymptote is a line, so you want to make sure you put a y equals in front of it. Okay, so make sure you put your slant asymptote in that form. But that slant asymptote is actually just the line, so this is a really special example. Alright, let's keep going, then we'll graph it. The y-intercept, you put 0 in for x, and if you go right to the reduced function, you get 0, 5. The x-intercept, you just look at the numerator factor that's left, and that would be negative 5, 0. So remember, x-intercepts come from the numerator only, the numerator zeros. Okay, So let's graph this. So what's this is going to look like is you'll have a y-intercept at 5, x-intercept at -5, and a hole at 611. And it's going to look like y equals x plus 5, so it's going to look like the line y equals x plus 5, except there's a hole at 611. Those are my favorite to do, even way back since high school. Alright, so let's look at another one. Alright, so we are going to talk about slant and horizontal asymptotes, but first we have to factor. Okay, so this one, notice that you can pull a 2 out of the numerator. So let's do that first, so then we can factor a little easier. You can also pull a 2 out of the denominator. So those 2's are constants, they can cancel. Alright, so now all we have to do is factor 2x squared minus x minus 6. So this one, you have a 2x and an x, so we're going to have to look at outer terms and inner terms, and we're going to have to figure out the factors of 6, 1 and 6, 2 and 3 that subtract to be 1. So we have to play around with this 2. So if I put a 2 here, my outer term is 4x. If I put a 3 here, my inner term is 3x, and they do subtract to be 1. We want it to be a -1, so we'll make that a -4x and a positive 3x. Okay, so the top is factored and the bottom is factored, and we've already canceled out the 2's. Now you can't cancel these out first yet. You have to get your domain. Remember, you got to get the domain before you do any factor canceling. Okay, so 2x plus 3 cannot equal 0 is going to give me x cannot equal -3/2. Okay, so your domain is -infinity and -3/2 union -3/2 to infinity. So once you write down that restriction, then you can cancel. And then because this factor cancels, it's going to show up as a hole. So this is kind of a hard one. A hole is an ordered pair, so to go get the x coordinate, let's write down the reduced function. There it is. That's the reduced function. So to get the hole, you just plug that into that reduced function. -3/2 minus 2 is -7/2. So there's your hole. Vertical asymptote, there are no more factors left in the denominator that did not cancel, so there's no vertical asymptote. Okay, now again, you might notice that this is the same situation that we had up here. This is going to look like a line with a hole in it. So the slant asymptote is going to be y equals x minus 2. The y-intercept, put 0 in for x, you get 0, -2. Notice how I'm using the reduced function for everything. The x-intercept, you can look at that numerator, or you can put 0 in for y. The 0 in the numerator would be 2, so that's your x-intercept. And it's going to look very much the same as that. It's going to be a line with a hole. Okay, so those are two interesting ones where the slant asymptote is the reduced function, but that doesn't happen all the time. So let's take a look at number 3. So we got a factor. So factors of 6, 1 and 6, 2 and 3. That subtract to be 1 would be x minus 3, x plus 2 over x plus 5. And so you can see nothing cancels this time. So our domain restriction, x cannot be -5. So that means that -infinity to -5 union -5 to infinity are all the x's that can be in the function. And since this factor doesn't cancel, there is no hole this time. And there is a vertical asymptote this time. Okay, so now it's time to look at the horizontal or slant asymptote. Notice that you have a degree 2 over degree 1. So that's large over small, and what happens is if you put a million in here in the numerator, a million squared is a huge number. It's a 1 with 12 zeros over a million plus 5. And so for large values, these small numbers don't really matter. What you can see is that this numerator is going to get bigger and bigger and bigger and bigger at a much faster rate than the denominator. So that's why you will have a slant asymptote here. And to find the slant asymptote, you can divide, long division, or if this is a 1 x to the 1 term, you can use synthetic division. So that's what I'm going to do here. So remember, you put the 0 in the box, and then 1 is your x squared term, negative 1 is your x term, negative 6 is your constant term. This 1 comes down, 1 times negative 5 is negative 5. Add those, you get negative 6. Multiply those, you get 30. And you get a remainder of 24. Now this is a different context. Usually that's bad if you have a remainder, but we're just talking about in behavior. So that means we can just not worry about the remainder. So what is this 1, negative 6? Remember, synthetic division, it goes down 1. So this is x minus 6. But remember, your slant asymptote isn't x minus 6, that's an expression. The slant asymptote is a line, so you have to put y equals x minus 6. Okay? So you get the slant asymptote by dividing. You ignore the remainder. Okay, now back to this. We have a little bit more tricky y-intercept because you don't have a nice reduced function. So remember, you're just going to have to put 0 everywhere you see an x. So y equals 0 minus 3 times 0 plus 2 over 0 plus 5. So that's negative 6 over 5. So that's your y-intercept. Your x-intercept, remember, it just comes from the numerator. It's the zeros of the numerator. So you've got 3, 0 and negative 2, 0. Okay. So let's look at that graph. Okay, so I put this into Desmos, and you can't see some of the negatives, but and you only see one branch. Well, that's not actually very accurate. So let's go ahead and put in the vertical asymptote, x equals 5, and let's put in the slant asymptote. Alright, and let's make those dashed. And we have our y-intercept. There it is, 0, negative 1.2. And we have our x-intercept, 3, 0, and negative 2, 0. So if you were graphing this on your paper, that would be enough to graph this branch, because you can use your knowledge. You know that as x gets closer and closer to this negative 5, it's going to hug that vertical asymptote. And now you know that as x gets bigger and bigger and bigger and bigger, it's going to get really close to this slant asymptote. But to get the other ones, which is why we're not doing this by hand right now, you have to just plot points. There is another branch down here, and you could use the table setting of your calculator and put in negative, negative 6, negative 8, negative 10, just to get an idea of where this is going. But this is what your graph would look like. So see, as x gets really, really big, see how it hugs that slant asymptote? So that's what's going on with that one. Okay, let's look at another one. Here the denominator is already factored. The numerator is going to factor into 2x and x, and the factors of 12, 1 and 12, 2 and 6, 3 and 4. Because we don't have a nice 1 there, we've got to look at outer and inner terms. So I want the outer and inner terms to subtract to be 5. So if I use 4 here, that gives me 8x, and 3 here, that gives me 3x, and that's going to subtract to give me 5. Now I want it to be a negative 5, So -8 and +3 would work. So those are my signs. 2x plus 3, x minus 4. Okay, now remember, before you cancel anything, the domain is just going to come from the zeros of the denominator. X can't be 4 or -1. So you have an interval notation of -infinity to -1, union -1 to 4, union 4 to infinity. But now we can cancel, and we'll write down the reduced function. So this is one where you have a hole, because that factor in the denominator got canceled. How do you find the hole? Well, a hole's an ordered pair. So you put this x equals 4 in here. We have a calculator for that. You just got to understand the concept. So 2 times 4 plus 3 over 4 plus 1 gives you, messed up. There we go. 11 over 5. So there's our hole. Vertical asymptote, this one has a vertical asymptote because this factor didn't cancel, so there's a vertical asymptote, x equal -1. So both of these restrictions are showing up in two different ways. Now, is this going to have a horizontal or a slant asymptote? Well, you can see the degree here is 2, and if you multiply this leading term times that leading term, that's degree 2. Or you can look at the reduced function, degree 1 over degree 1. And so if you have the same degree, y equals the leading coefficient over the leading coefficient. So y equals 2 would be my horizontal asymptote. So no slant asymptote on this one. The y-intercept, you put 0 in for x, so that gives you 0, 3, because that's gone and that's gone. The x-intercept, you look at the numerator 0 only after canceling. So that's going to be -3/2, 0. Okay, so I graphed this one, and it looks very normal, like a typical rational function with two branches. You've got the vertical asymptote x equal -1, the horizontal asymptote y equals 2. And Desmos doesn't do a great job of showing you the hole, but if you hover over it, and sometimes it's a little tricky, hover over it, you might see that it is saying that when x is 4, it is undefined, and you can see the hole there. Okay, so this if I hold my mouse button down, that's what your graph would look like. Okay, last one, 2x minus 3 over, got a factor, 2x and x, factors of 15, 1 and 15, and 3 and 5. Got to do outer and inner terms. The factors of the outer and inner terms that subtract to give me 7. So let's try 3 and 5. So if I put a 5 here, that gives me 10x. If I put a 3 here, that gives me 3x. And they subtract to give me 7. I want it to be a positive, so I need a positive 10x and a negative 3x. Okay, so your domain before you cancel, x can't be 3/2, that's the 0 here. X can't be -5, that's the 0 there. So make sure you go in the right order. The domain is the set of numbers it can be, so that's -infinity to -5, union -5 to 3/2, union 3/2 to infinity. All right, now we can cancel. Now I'm doing this example because I want to show you what will happen here. These two factors cancel, and nothing is left in the top. Well, remember, there's always an understood 1, so you can't forget that. So your reduced function is actually 1 over x plus 5. Okay, so that 1 will pop up. All right, so since that canceled, that means there's a hole at 3/2 something. And don't panic about this. You've got a calculator. You just need to know the concept. You put that 3/2 in for x here to find the hole. So 1 divided by 3/2. I'm using the sideways division key, so that's why I had to use parentheses. 3/2 plus 5. And you get 2/13. If you hit that little squiggle, it'll make it a nice rational number. So there's your whole. You also have a factor that does not cancel, so that's going to be a vertical asymptote at x equal -5. Alright, and so the other thing I wanted to do is, we haven't done one like this. This is a degree 1 over degree 2. So this is what we say a degree small over large. And then when that happens, the denominator is just getting huge as x gets really, really, really large. So y equals 0 is your horizontal asymptote. Okay, your y-intercept, remember you can use the reduced function. The y-intercept, you put 0 in for x, and if you put 0 in for x here, you get 0 1/5. The x-intercept, this is again why I'm doing this one, there is no 0, there's no factor in the numerator. 1 obviously doesn't equal 0. So this does not have an x-intercept. Okay, so I graphed this one. It has a vertical asymptote at x equal -5 and a horizontal asymptote at y equals 0, and then your typical 2 branches. But then remember also it has a hole at 3/2, and it's undefined there. I just can't, there it is. 3/2 2/13. So if you wanted to check that, you could type in the order pair 3/2, comma 2/13, and it's going to show up as a dot. But then what you can do is make that look like a hole, and so then you've got it, and it's in the right spot because it's on that green branch, I mean the red branch there. Okay, so I'm in the lab manual and we are going to actually graph one. This is right now my page 134. It's in unit 3, the table of contents, rational functions, and there's plenty for you to try, so I would try them. And I also wanted to show you that you're not always going to have that little reminder template. You have to remember, we'll tell you what to find, but you won't have the position to remind you. Remember, you want to find the domain first, and the domain comes from the denominator. The restriction on that would be the 0. X cannot be -2, so the domain would be -infinity to -2 union -2 to infinity. Then next you want to see if the factors cancel, and no factors cancel, so there is no hole. So that restriction's got to show up somehow, and it's going to show up as a vertical asymptote, x equal -2. Okay, so once we do that, then we can also look at the horizontal asymptote. So this is an interesting one. What is the degree of the numerator? Well, this numerator is 3x squared. The denominator is x to the 1. So that's a degree large over small. And this is rarely is this unfortunate, but it's already factored. So before we can find the slant asymptote, you're going to have to multiply this out. So 3 times, if we multiply that out, that's x squared plus 4x plus 3 over x plus 2, which is 3x squared plus 12x plus 9 over x plus 2. So that's what your function is. So to find the slant asymptote, you're going to have to divide. I'm going to use synthetic division. So I'm dividing by x plus 2, but my little algorithm tells me put the 0 in there and then put the numbers 3, 12, and 9 in there. So if I bring down the 3, multiply, you get -6. Add, you get 6. Multiply, you get -12. 9 minus 12 is -3. You have to understand the concept. Remember, the remainder does not matter. Okay, so this was a 3x squared term. This was an x. That was a constant. So this means that this is your expression, 3x plus 6. But the slant asymptote is an equation of a line. So that's y equals 3x plus 6. Okay, so we've got the slant asymptote, vertical asymptote, whole, domain. Now remember, you just look at find the y-intercept. Now since you've multiplied it out, the y-intercept might be easier to find looking right here, because that's going to go to 0, that's going to go to 0, that's going to go to 0, and you're just left with 9 halves. And the x-intercept would be better to look at the factors of the numerator. So you've got x-intercepts at -3, 0, -1, 0. So both of these has benefits. Okay, now we said we'd graph it, so let's do that. So we'll graph the x-intercept, -3, 0, -1, 0. The y-intercept, that's 0, 4.5. Slant asymptote. So you might want a quick lesson on how to graph lines, y equals mx plus b. That's 6. That b is the y-intercept. So 6 is the y-intercept. And the slope of this slant asymptote is 3 over 1. So you can rise 3 and run 1. Or you can go down 3. Okay, so this is your slant asymptote. And I really should have done that first. That's something I should tell you. Always do your asymptotes first. All right, x equals -2 is your vertical asymptote. Okay, so I'm just going to redo these so you can see. So that's how you start. Okay, now when we graph these zeros and these y-intercepts, you might need a few more points to get a really good graph. Okay, so just look at what else you want to see. I want to see what happens at x equals -4 and x equals -5. And maybe, I know what's going to happen here, but maybe -1.5. And that might be like a tall order. It would have been a tall order before I decided this semester to just use the table function of the calculator. So let's put the function in. So clear that, and function is 3 parentheses x plus 3 parentheses x plus 1 and then x plus 2. And then all you have to do is hit enter, and then it's going to say auto or ask or x equals question mark. Let's just do that, and then we'll just put the values we want. So I want a -4 and a -5 and a -1.5. Okay, so at -4 we've got -9 halves, which is -4.5. And at -5 we've got -8. And at -1.5 we've got -4.5 again. So if we plot these points, so -4, 4.5, -5, -8, you can see what's happening. As x gets close to -2, we know what's going to happen. It's going to hug the vertical asymptote. And you can see that it's trying to hug that vertical asymptote. And then at -1.5, we've got -4.5. And you can see what's happening there. As x gets bigger and bigger, it's going to hug the slant asymptote. And as x gets closer and closer to -2, it's going to hug the vertical asymptote. So that's how you would graph one of these functions. Continue to practice and check your key.